Let's look at inverting a 2 by 2 matrix. Let's say that we've got matrix A as A, B, C, D and matrix B is P, Q, R, S. If we say that B is the inverse of A, if it exists, then AB must equal BA, which equals the identity matrix. Let's write that in matrix form. So in matrix form, ABCD times PQRS would equal the identity matrix. Let's times those matrices together. So timesing the matrices together, we would get AP plus BR, AQ plus BS, CP plus DR, and CQ plus DS equals the identity matrix. So we've now got 4 equations that we can then solve. We've got this equation, this equation, this equation, and this equation equals these numbers. So these are our 4 equations. AP plus BR equals 1, AQ plus BS equals 0, CP plus DR equals 0, and CQ plus DS equals 1. And we really want to know, what does P equal, what does Q equal, what does R equal, what does S equal in terms of A, B, C, and D. And that's what we're going to do now, but with some basic manipulation. So here are our equations again, and let's start manipulating them. Looking at equation 3, if we rearrange equation 3, we can make P the subject, which gives us minus dr over C, and we can substitute that into 1 to eliminate P. We'll get A minus dr over C plus BR equals 1. Remember, we're trying to find out what P, Q, R, and S is, so we're happy for A, C, and B to still be here. Making a common denominator of C, we get minus ADR plus BCR over C equals 1. And therefore, we can take R out as a common factor on the numerator. So we get minus R, AD minus BC, the determinant, over C equals 1. R equals minus C over AD minus BC. And we can substitute that into equation 1 again to find out what P is. P is going to be D over AD minus BC. Let's do a similar thing to work out Q. So equation 2 gives Q as minus BS over A, just by rearranging equation 2. And if we substitute that into equation 4, we will get C times minus BS over A plus DS equals 1. So A would be our common denominator, which gives us minus BCS plus ADS on the top over A equals 1. S is the common factor this time, so we've got S bracket the determinant over A equals 1, and therefore S equals A over DD minus BC. And we can then substitute S back into equation 2 to work out our Q, and we will get minus B over AD minus BC. Obviously, all of these are only valid when AD minus BC does not equal 0. 4 equations for R, P, S, and Q, which is true when the determinant is not equal to 0. So we can rewrite that matrix P, Q, R, S in terms of those. And we get this big matrix here, and that's true when AD minus BC doesn't equal to 0. But since the denominator is the same for all of them, we can take that out as a common factor. If we do that, we get 1 over the determinant, D minus B minus CA, provided that the determinant doesn't equal 0. So what have we found out there? We have found out that when the determinant doesn't equal 0, the matrix A, B, C, D does have an inverse, which is denoted A minus 1, or A inverse, and A inverse was equal 1 over the determinant times D minus B minus C and A. So here is the big idea. If you've got a matrix, let's call it M, M times M inverse would equal the inverse of M times M, which equals I. And in the big black box is everything we need to know. If A is this matrix, the inverse of A is 1 over the determinant times D minus B minus C A. A inverse is the inverse of A, so that if we did A times X equal to Y, then A inverse Y would equal X. Or A times A inverse equals A inverse A, which equals I. So if we had A equals A, B, C, D, to find the inverse of A is quite easy. We just do 1 over the determinant and the ones I always do first are this diagonal. They get swapped. So D and A. These do not get swapped, but you put a minus on them. So minus B minus C. Let's practice that with some numbers. So the first one, 2, 0, 0, 2 inverse. So I need to do 1 over the determinant, which is going to be 2 times 2. Swap the diagonals, put a minus on these, but these are 0, so it's just 0. There's our inverse. Let's do the second example. We've got 1 over the determinant, which is 4 minus 6, which is minus 2. So minus a half. Swap these ones and put a minus on the other two. And that will do. We could tidy that up by not having a minus outside. So for half, minus 4, 2, 3, minus 1. And the last one, 1 over the determinant. Well, the determinant is minus 21. Take away 2 is minus 23. So minus a 23rd. Swap the elements. Minus the other two. Tidying it up by making it a positive fraction. We get 3, 2, 1 and minus 7. Okay, an example. For what value of p is this matrix singular? Given that p is not this value, find the inverse. So a reminder, singular means it has not got an inverse. The determinant is 0. Non-singular means it does have an inverse and the determinant is not 0. So for singular, the determinant of this matrix must equal 0. So that implies 4 times 3 minus p plus 2 times minus 1 equals 0. 12 minus 4p plus 2 equals 0. 14 minus 3p equals 0 implies 3p is 14. So p is 14 thirds. And the next part of the question, given it is not this value, find the inverse. So if it's not that value, it's any of these values, so we'll just do it algebraically. So the inverse, remember, is 1 over the determinant. Well, we already know the determinant because we did that and that already here. It's 14 minus 3p. Times, swap these two, put a minus on the other two. And we're done. Okay, a few matrix proofs involving the inverse. So, if p and q are non-singular, prove that pq inverse equals q inverse, p inverse. We don't have to draw any matrices here, we just have to use matrix algebra to solve this. So let's say let the matrix C equal pq inverse. Just recall, if you times a matrix by its inverse, you get the identity. Okay, which means if I do PQ, which is the inverse of PQ inverse, and times it by C, I will get I. So let's eliminate P. P inverse P QC must equal, doing the same with the right hand side, P inverse I. You can always eliminate a matrix by timesing by its inverse. Because P inverse P is I times this is QC. So we've now got QC equals, well, P inverse times the identity is just P inverse, because it's a matrix. And let's do the same trick again. So going up to here, Q inverse QC must equal Q inverse P inverse. Q inverse Q is just I, so we've got IC equals Q inverse P inverse. So we've got C equals Q inverse P inverse. Or to put it another way, since we know C is PQ inverse, we've just done PQ inverse as the inverse of Q times the inverse of P. So we've got, if A and B are non-singular matrices such that BAB equals I, we have to prove that A equals B inverse B inverse. So we'll start with the first statement and try and get to the second statement. We've got BAB equals I. Let's eliminate that first. B then. just times it by the inverse. B inverse B, AB, equals B inverse I. Well, B inverse B is always I, so that gives me just AB on the left. B inverse times the identity is just B inverse. So now, since we want to have A on its own left-hand side, we can just times this side by B inverse. So we've got A, B, B inverse equals B inverse times another B inverse. That implies that A equals B inverse, because this is just the identity times A, which is A. A non-singular matrix F satisfies this equation where I is the identity matrix. We have to show that the inverse of F is this. Again, we've not got any actual matrices here, so we're going to just use matrix algebra to show this. Let's start off with F squared equals 3F minus 2I. Well, if I times this side by the inverse of F, I can times this side by the inverse of F. So let's try that. F inverse F squared equals, well, 3 F inverse F minus 2 F inverse I. I'm timesing all elements by F inverse. Notice that these 3 and 2 are scalars, so we can just jump in front. It makes no difference. But the order here has to stay consistent. I was on the left, so I'm on the left of this matrix. I was on the left, so I'm on the left of this matrix. F inverse F is just I, so that just leaves F on this side equals 3 times I. Now I need to write I because 3 is just a number. 3I is a different thing. That's going to be 3 times the identity matrix. Minus, but now I've got a matrix times I, which is just the matrix, 2F inverse. Can rearrange that to make F inverse the subject. So let's move F inverse over to this side. We'll have 2F inverse equals 3I minus F. Dividing through by 2, we get F inverse equals 3 over 2I minus a half of F, as required. The last thing I'm going to look at is solving equations using the inverse. So let's say we've got these two equations and we want to solve them using matrix multiplication. So let's set up our matrices to see how this works. We've got 2, 3, 1 minus 1, and we've got, that's going to be x and y, and that equals 1, 3. So remember, we could just call this matrix A, and this matrix B, and this matrix C. And essentially what we're saying is A times B equals C, right, as a matrix. AB equals C. I want to know what B is though. So I can get rid of A by times it by A inverse on this side. A inverse AB equals A inverse C, or in other words, B equals A inverse C. So if I can work out the inverse of A, times it by C, that will give me matrix B, which will tell me what x and y is. So let's just do that now. Inverse of A, remember, is 1 over the determinant. So I've got minus 2, take away 3, which is minus 5, so minus a fifth. Swap these elements, put a minus on the rest. So A inverse C equals minus a fifth, minus 1, minus 3, minus 1, 2 times 1, 3. That's minus a fifth times, but it reminds us of matrix multiplication, row times column, so it's minus 1, minus 9, that's minus 10 for the first element, row times column, so that's minus 1 plus 6, which is 5. Dividing through by minus a fifth, we get 2 on the top, 5 divided by 5 is 1, and minus 1 on the bottom, so that tells us x and y. X is 2, y is minus 1. X equals 2, y equals minus 1. This has been Claire on Maths. Today we've been looking at the inverse of a 2 by 2 matrix. We've proved where it comes from and we've solved some problems with it. Take care, stay safe, and goodbye.